So in this video, we are going to talk about other common functions that you would run into. And so we're going to set it up. A function f of x of the form a number times x to the n, where a is some real number and n is some natural number. So we want to have the scenario where the exponent is odd, okay? If the exponent is odd and we have some, maybe a here is equal to 1, all right, the domain and the range for these functions is all real numbers. So you look at x, f of x equal to x is just a line, okay? This is linear. It's a line, okay? The power is 1. It's 1 as an odd number. You think about the domain, all the x's we use every single x. You think about the range, we go from negative infinity up to positive infinity. Now, what's the big difference between a cube and a linear? So instead of having the line, it bends a little. Where does it bend at? It looks like it's bending around the origin here, okay? And what's happening here is we're actually increasing our multiplicity, and we'll talk about this later, but the increasing of the multiplicity, what it ends up doing is it makes the curve flatten out. At the 0, okay? So the higher this degree is, the more the curve flattens out. So degree 5 is going to flatten out more than the cubic even. So this is a cubic, degree 3 there. It's odd. Odd tells me something. If I have an odd exponent, that tells me that my end behavior is opposite. Odd is opposite. Okay? Meaning if one side goes to positive infinity, the other side has to do the opposite, is negative infinity. Same here, if it's negative infinity, the other side's positive infinity. And positive infinity here means negative infinity here. It's the opposite, okay? If the coefficient in front is positive, that means the right-hand behavior is going to go up to positive infinity, just like that, okay? So if you had like f of x, say you had a f of x equal to like negative x to the 5th, okay? So how would that graph look? Well, instead of going up to positive infinity, it's going to go down to negative infinity, okay? And then since it's an odd power, if one side is a negative infinity, the other side has to be a positive infinity behavior, okay? So it's the exact opposite when you have the negative versus the positive, okay? So say instead we have an even exponent. Even exponents typically have a domain of all real numbers, so any x's work, all the x's work. Okay, but the range is a little bit different. The range goes from 0 to infinity, 0 to infinity, unless you have some vertical shift, which takes the parabola and shifts it down or whatever. If there's no vertical shift, then what you're dealing with is a range from 0 inclusive to infinity, okay? Now x squared, we come down, we touch the x-axis, and then we come back up. When I see an even exponent, so squared to the 4th, to the 6th, and so on, those are even. Even exponents are the same. Even means the same. What does that mean? If one side goes to positive infinity, the other goes to positive infinity. Positive infinity here means a positive infinity there. And last, if it's positive infinity here, it's positive infinity there. Like if you graph this, and maybe you had like an f of x equals, I don't know, negative x to the fourth, instead of being going up to positive infinity, it's going to go down to negative infinity. But since it's an even number, that tells me that the other side has to agree with it, so it's also going to negative infinity. Okay? So the negative coefficient in front tells you if it's happy or sad. If it's a negative number, it's sad. And if it's a positive number, it's happy. Okay? We're smiling. All right? Okay. Now, if we have, instead of being of the form a times x to the n, say we're of the form a number divided by x to the n. Okay, a number divided by x to the n. Or a times x to the negative n. Remember your exponent properties. Okay? If the exponent is odd, same thing. Odd means opposite. Odd is opposite. So the opposite here, if one side is going up to plus infinity, that means the other side is going down to negative infinity, just like this. Okay? Now, why do we have this asymptote looking thing? Well, this is raised to the 1 power here. Okay? Here's the idea. Okay? If I have 1 divided by x, the one number I can't divide by is 0, so I set the denominator equal to 0. X equals 0 cannot be in the domain. That's what this says right here. I take all real numbers that are negative, all real numbers that are positive, but then I'll leave out the 0 in the middle. Okay? And then same thing with my range, right? If I have a 1 in the numerator, 1 can never equal to 0. The only time a fraction can equal 0 is this the numerator, the top part equals 0. So it can never be 0 and it can never divide by 0. Okay? And since it's opposite, if one side's positive infinity, the other side's negative infinity. And so what happens is I increase this power, so it goes from 1 over x to 1 over x cubed. The only difference is the curve gets closer to the axes. Okay, as you can see, the power increases, the curve gets closer to the axis. Okay? Now, if the number is positive, okay, then on the right side I have positive infinity. But if it's a negative number up top, okay, then that tells me that on the right side, I'm going down to negative infinity. I'm literally taking my graph that's over here and I'm flipping it down. I'm reflecting it across the x-axis. That's what multiplying by that -1 does. And then the same thing here. I'm taking this graph here and I'm flipping it up to the top. Okay? And so that's what's happening with this. This is going up to positive infinity. This one's going down to negative infinity. Okay. Now, say instead of being an odd, I have an even exponent. So even means the same. So if one side goes up to positive infinity, the other side goes up to positive infinity. And if one goes to negative infinity, the other side goes to negative infinity. Okay, so they're the same because they're even exponents. So 1 over x squared. So they're both going up to positive infinity here. All right. If I change it from a positive to a negative, it reflects across the x-axis. So it reflects downwards like that. Okay. And they're now both going to negative infinity. Here we have a positive 1 coefficient up front, so it's going up to positive infinity. And since it's even, it agrees on the left and the right. Okay. So the right-hand behavior going to positive or negative infinity is determined by the coefficient you're multiplying by. If it's positive infinity. If it's negative infinity here. Once again, thou shalt not divide by 0, can't divide by 0. So I'll leave the 0 out of the domain. And then the range here is only positive numbers, okay? Unless you flip it down by multiplying by that -1, then it becomes only negative numbers. So these are different types of rationals. Okay. We call this a line, linear. This is a cubic. This is actually a quaternion. No, it's not a quaternion. That's a quintile. I don't know. Something with 5, power of 5. Who knows, right? Raised to the 5th power. This squared is a quadratic. To the 4th is a quartic. Okay. To the 6th, I don't know if that one has a number or not. Okay. Or a name. Down here, now we're going to deal with radicals. Okay, so raising to the rational exponent, if I use my rider and the horsey rule, the rider goes in the house and the horsey goes outside in the barn, right? And so I have a and then the nth root of x to some power. Now, if n is a natural number and it's odd, okay, it's opposite again. So if one goes to positive infinity, the other goes to negative infinity. If n is equal to 1 here, then you're just dealing with a line x. Okay? If n is equal to 3, that's the cube root. The cube root goes to positive infinity on this side, and it goes to negative infinity on this side. It's the mirror image. Okay? The 5th root, the only difference between that and the cube root is it's just a little bit lower. That's the 5th root. Okay? If I go even higher roots, that's the 7th root. The higher my root is, the lower my curve gets, the closer it gets to the x-axis. Okay, that's the idea. All right? So positive infinity to negative infinity. Now, if the root is even, this kind of restricts things, okay? The good thing about odd roots, I can take the cube root of a negative number. I can take the cube root of -1 and get -1, can't I? Okay? I can take the 5th root of -1 and get -1. All right, so it's -1 times -1 times -1 gets you -1, right? Same thing with to the 5th root, you just write it 5 times. But the even does not work for negatives, okay? Not real for negative numbers. Okay, it's not real for negative numbers. So we're only going off on one side here. Now the only difference is as my index increases from 4 to 6 to 8 and so on, the steepness, okay, it gets steeper. All right, let me actually try to draw this a little better. So if this is the square root, so that's the square root of x. So the 4th root might look like this. The 5th root, I'm sorry, the 6th root might look like this. Okay, and so you're passing, each one is passing through this point right here at 1, 1. Okay? And so as you increase the root, the more flat the curve gets. Okay? So the last thing right here, we'll talk about all of this stuff in another video. Okay, so that kind of covers your square roots. So your square roots and your cube roots. Okay. What about absolute value? Absolute value. This may not pop up, but just in case it does, I want you to know what the absolute value function is. Absolute value is the distance from 0. Okay? So if I say the absolute value of 5, how far is 5 from 0? Okay? Well, the answer is 5. But what if I did the absolute value of -2? How far is -2 from 0, right? So if you look on a number line, it looks like the distance from 0 is equal to 2. So this is equal to 2. So the absolute value bar, that just basically, it gets rid of negatives is the easiest way to think about it. Okay? So what does this look like? All right, this is defined to be the absolute value of x is equal to x. So it's equal to the number when the number is greater than or equal to 0. So if it's a positive number, I just write the number. However, if it's a negative number, I got to get rid of the negative. Well, I can get rid of the negative by multiplying by a negative. So that's what I do there. So if that's the case, like this one right here, absolute value of -2, this is equal to negative of -2, which is 2. Okay, so that's the idea of a piecewise function. This is what it is, and this is where it's true. So I use the second part here because -2 is less than 0. Okay, and that's what I plugged into my function, f of -2. All right. Now, what does this graph look like? The graph says I want to graph x for greater than or equal to 0. So if I graphed x, this is what x would look like. This is f of x equals x. But it's only going to be for values that are greater than or equal to 0. Okay? And then I want it to be -x for less than 0. Well, -x looks like this. Okay, this is f of x equals -x. And so what that's going to be is only for values that are less than 0. So then I can just get rid of this other stuff here. Okay, and so the absolute value makes a V. So that's what I want you to think of when you see an absolute value graph, you do a V. And I think we can do it on the calculator. Let's see if we can do it on this one. So I'm going to go to graph, and I'm going to see if I can do math. And let's see, can I do absolute? Yeah, let's do absolute value, and then X, and then enter, and you see the V. So that's a weird looking V, but that's the V, all right, that I'm talking about there. So you can take f of x and you can actually do transformations to it. So if I do -2 times the absolute value of x, what does the -2 do to my V? Well, the negative reflects it downwards, but then the -2 makes it more narrow. Okay, so my new graph is going to look like this, going down at a slope of 2. Okay? And we'll talk about reflections in a later video. But those are all the different common functions you'll